All right, so we're going to be looking now at convergent and divergent fractions. So how do you know, just by looking at it, if it's going to be convergent or divergent? So we're going to do a few examples, and then I will tell you how you can tell if you don't figure it out before I do. All right, so we're going to do a few, and then everything should work. So we're going to go from t to infinity, because it's at the top. So 1 to t. And then now we're going to do our integral, and then plug it all back in. So integral 1 over x to the half dx. This is integral of x to the negative half. And we really want to rewrite it so that you can see what's going on with these problems. Okay, so we're going to add 1. So if we add 1, that would be a half, and then we flip it. So we get 2 x to the 1/2. So this would now be the limit as t approaches infinity of 2 x to the 1/2 t and 1. And then we plug that in. Zoom in now, or we'll just leave it. Limit as t approaches infinity like that. All right, and now you can probably notice here, if I were to plug t into here, this is a radical, and if you remember how square roots look, they go off to infinity. So this is going to go off to infinity, which means it's divergent. All right, let's try another one. All right, so this would equal the limit as t approaches infinity. And then this one's nice and quick. We just say ln of x, right? So this would be the limit of ln of t, the absolute values, there we go, minus ln of 1. And so ln of 1 we know is 0. And if you remember the limit as t approaches infinity, it goes off to infinity. So remember, it looks just like this. So we're going to just go the top part. As it goes infinity, it goes infinity. So this is also infinity, which means it's divergent. Does that mean they're all divergent? So if you notice, what I'm doing here is I'm adding numbers to the exponents. So we started with a half, and then a 1, and now we're going to look at 3/2. So we are going somewhere with this. So t approaches infinity. Because what we're trying to do is find a pattern here that if you follow it with a fraction, that we end up with something we can look at and know what's going on. So again, I want to always take my time on these because I want you to see what's going on here. So this is integral of x to the negative 3/2 dx. And again, we're going to add 1, which means this would be negative 1/2. So we end up with x to the negative 1/2. And if you flip that, we get negative 2. So this is the limit as t approaches infinity of negative 2 x to the negative 1/2 t and 1. Now, if you remember with negative 1/2, that means it's a denominator. So when I plug t into it, it's going to look like this. Plus 2 now, because it's a minus. And then square root of 1. So this becomes a square root on the denominator, and I plugged a t into it, and then I plugged a 1 into it. So that becomes 2. Well, what's that become then? T's on the bottom. Do you remember our whole limit thing? When you have a fraction down here, this goes to 0. So we end up with just plain old 2, which means this is convergent. It converges. So first one diverged, diverged, converged. So let's do one more just so that we have a nice clean pattern here. And I want to show you the rule, which you can already see. So this is the limit as t approaches infinity from 1 to t of 1 over x squared dx, just like that. And so we do our same thing. Integral of 1 over x squared dx would be the integral of x to the negative 2 dx. And again, we add 1. So that would be x to the negative 1, and then we flip it, so negative 1. So limit as t approaches infinity of negative 1 over x, t and 1. So we're getting that fraction again. See, it's negative 1. In fact, let's write it with a negative 1, and then we'll plug it in at the end so that we can see what we're looking for. So limit as t approaches infinity of negative 1 over t plus 1 over 1. And then again, so again, all I did was flip that. I put it down as a denominator, and I plugged a t into it, and then I plugged a 1. And this goes to 0. So the answer is 1. So convergent. So it went, if we made the fractions exponent a little bit larger. So if it was, we had a half, it was divergent. That's a 1, right? Right there. So if the denominator had a degree of 1 for that polynomial, we get divergent. And then 3/2 convergent. And then 2 convergent. So somewhere in here is where we had our split. This is the divergent. And then everything after that is convergent. Well, if you look at it, what's happening here is at the very, very end. When we have our limit here, we're getting stuff that is not a fraction. But right when we passed a certain number, we ended up with fractions. And those fractions are now going off to 0. So if you think about it, what happens is we add 1 each time. We add 1. And we add 1, and when we get something that's convergent, then when we add 1, we still have a negative exponent, which will convert it back to a fraction. So we're looking for, after we take the integral, that we end up with a -1. Well, the only way to do that is if you were to add 1 to something, then that denominator has to have a negative that is bigger than 1. So what we're saying is if that denominator has an exponent that's bigger than 1, it's going to converge. And if the denominator has an exponent that's less than 1, it's going to diverge. And it's of this form, by the way, the 1 over x. We could put a 2 there, or a 3, or any other constant we want. But that x has to have an exponent that is bigger than 1. So if we call that a p, if our p is greater than 1, we're going to get converge. And if our p is less than or equal to 1, it's going to diverge. And the reason I can say equals 1 is because that's what we used here. If you look at the second one, it's a 1, right? And so it diverged. So anything less than 1 at the denominator, when we add the 1, it's going to turn it into a non-fraction, right? It's going to bring it right back up to the numerator, and then it's going to go off to infinity or negative infinity, and it's going to diverge. But if this is less than 1, or greater than 1, then when we add the 1, it's still going to remain negative, which means it'll still remain a fraction, and so it'll still go off to 0 when our t goes to infinity or negative infinity, and we're going to get something that converges. So let's take a look at Desmos, and you'll see some pictures of this. So our first one was 0.5. That was our denominator here. I can change my n now to any exponent I want. And you can see there's my graph at 0.5. And so right now I'm already at 600. Let's look at the integral. So my integral, you can see, just keeps getting bigger and bigger, bigger and bigger. It's going off to infinity, which means it's divergent. And so if I make it 0.9, that's less than 1. And you can see it still has the same thing. Keeps getting bigger and bigger and bigger and bigger and bigger. And if I make it 1, keeps getting bigger and bigger and bigger. It's still growing. It's growing slower. You can see it's just kind of slowing down as we make the exponent. But now if I just go a little bit over 1, like 1.2, look at it. It's slowed down. It is actually converging towards a number. So our 1.5 that we did, look at it. Remember we got 2? Look at the number. See how it's just going 9, 9, 9, 9, 9. So if I were to plug in 2 for my square, we got 1. And you can see, watch the number. We just keep adding 9s to it. The 9 just keeps clicking away. 9, 9, 9, 9. So it's adding more 9 decimals as we go off. And that's 1. So if I had done 3, a cube, so 1 over x cubed. So that'd be 1 over x cubed. Right? Look at it. It already gave up and says it's 0.5. So yeah, so if it's 3, it's 0.5. So if that denominator's exponent is bigger than 1, 1.1, 1.0001, doesn't matter, bigger than 1, it's going to converge. And if it's less than 1, it will diverge. So see, even if I make my n back down, like 0.3, look at that, it's really high, right? 0.5, there we go, 0.3. Watch, it's going to go really quick. See how fast it just keeps going off to infinity. It's getting big, big, big. So the link for that is here if you want to play with it. It's in the notes. But yeah, if p is less than 1, it diverges. P is greater than 1. So we end up with this. So we have some fraction. So if we're starting with a fraction, some rational expression here, or just an algebraic expression with a denominator that has an x, a fraction, it is convergent if our p is greater than 1. So if this exponent is bigger than 1. So that way, when we add the 1 through the integral, it's still more negative, which will make it still a fraction. And if it's less than 1, well, it's not enough. So if it's less than 1, when we add the 1, it's just going to turn it positive, which means it goes off to infinity. So it needs to be bigger than 1 so that it'll be a nice large negative. I put 1/2 there, huh? Let's put 3. And so then that way when you add the 1, it stays negative, stays a fraction. All right. So on this one, would it be convergent or divergent? With this fraction right here, the integral from 1 to infinity of 1 over x to the 1.01001 be convergent or divergent? Yes, so 1.0001 is greater than 1, which means this is convergent. So let's try it here. Now it works the same way. If you think about it, I'm going to show you a picture of it with the Desmos graph. So we know that the 1 over x squared right here is actually going to be bigger than this because the plus 3x is just going to add more to the denominator, making it smaller. So this has to be bigger. And we know that this one's going to converge because our p is greater than 1, right? It's a 2. So we already know that's going to converge. So you can see if this one is going to converge, then the one below it also has to converge. Look at it. If you see here, how is it always bigger? It looks like they're the same, right? But if you zoom in, you can see, yes, the red is bigger than the green. So if this one's converging, so is this one. So now let's just prove it and find out what the answer is. All right, so this equals the limit as x approaches infinity, not x, t, from 2 to t of 1 over x squared plus 3x dx. So we need to find that integral. So our integral of 1 over x squared plus 3x dx. And we can use partial fractions. So 1 over x plus 3 would be 1 over x plus 1 over x plus 3. And then we call that an a and that a b. So there wasn't 1 and 1, it was a and b. So we get a x plus 3, b x. So ax plus 3a. Didn't write the x. Bx. And then this has to be 0 and 1. So we can see that 3a equals 1 and a plus b equals 0. So a equals 1/3. So b equals negative 1/3. So that means that we really have here is the integral of, I'm going to put the 1/3 on the outside. So a here is positive 1/3, b here is negative 1/3. And so we end up with 1/3 over x, we just put it on the outside. So this would be 1 over x minus 1 over x plus 3 dx. And so now we can find the integral of that. So it's 1/3 ln of x minus ln x plus 3. All right, so now we go limit as t approaches infinity of ln x. And there's a 1/3, so we'll just click it on the outside like that. T and 2. All right, and then now we just have to plug them in. All right, so we're going to plug the t in first, and so that would become ln t minus ln t plus 3 minus ln of 2, put it in parentheses, minus ln of 5, like that. So 2 would go in, 2 plus 3 is 5. All right, and then now if you look at this, we have the two natural logs, but what you have to do is put them together because this is like infinity, this is negative infinity. We need to see what their actual combination is. So this can be put together. It's t over t plus 3 and then same thing here, this would be 2 over 5. Like that. And if you remember with fractions, the t over t plus 3, they're both the same degree, so they're just going to go off to 1. And we can divide everything by t to show that, and that would go to 0. And so we'd get t over t, which is 1. But long story short, we get ln of 1, parentheses, parentheses, minus ln of 2/5. Now, 1/3 ln of 1 is 0, so we end up with negative 1/3 ln of 2/5. So what that means is it is convergent. So again, we started here to get this all worked out. This is just our scratch paper so that we could take this and plug it in here, but this is basically our work and what we're using to find out what it converges to, what is our integral. And we end up with this. Let's take a look at Desmos to see if this is correct. All right, so I have my A set at 2, and then now my B is going off to infinity. And I've already plugged in negative 1/3 ln of 2/5. We get this. And so you can see as we go to infinity, our integral is approaching it. So this is just our B value. That's it. If I bring it all the way back here, right? It's now at 10. So we're going from 2 to 10. That would be the integral. So the integral of this from 2 to 10 is this. And we're going off to infinity. And you can see it's approaching that same thing we were looking for. And since t is going off to infinity, t is going to be positive here. So we don't need the absolute values as well. We can change all those to parentheses. Let's look at our ti though. So I've already entered it in. That's our integral right there. What it was, 1/3 ln of x plus 3. So it's this one right here. And then our table set, we're starting at 2, and then we're adding 1,000. So you can look at it as we go all the way out. See, it's approaching what we were looking for, which is our negative 1/3 ln of 2/5. And you can check that in your calculator as well. So this is a nice little example so that you have it. But the main idea is to be able to look at a problem and go, okay, well, is it convergent or divergent? Because when you get down to this problem, you may think, oh, I see natural log. That's going to go off to infinity, so it's divergent. But you already knew it was convergent from the beginning. So that means it's now your choice and your turn to make it convergent, to show that it actually is convergent and to find that value. So use these to help you. If p is greater than 1, it converges. P is less than 1, it diverges. So see, we got our natural log here. We could just go on.